Welcome to the final sharp shorts on chemical nomenclature. At this point we're going to talk about covalent bonding and a little bit about binary molecular or binary covalent compounds. They are the simplest of the covalent compounds, and their naming, we follow the ionic naming with the binary molecular or put it in that same area because the naming is the same. Really very similar to binary ionic compounds. The difference is, of course, they don't have an ion or they don't form ions, so you're not balancing out cations and anions or positive and negative charges, which is what gives it its little twist. The rest of any organic naming, covalent molecular naming, we will save for another point. There are far more covalent compounds and molecular compounds in the world than there are inorganic ionic compounds, and they have their naming all to themselves. This is the one that matches. Anyhow, a little discussion of covalent bonding, just a brief overview. Covalent bonding as opposed to ionic bonding. In ionic bonding, you had ion formation by accepting or removing of electrons to form a stable octet, and then you would get a charge, and then you would get an electrostatic attraction between those charges. As illustrated by the water molecule here, what you can see is what you get here in covalent bonding is not ion formation, but a sharing of electrons in the valence shell that will allow each atom or element in there to get to its stable point. In the case of the oxygen, then, with its 2, 4, 5, 6 electrons all by the O's here, if it shares one with each of these hydrogens, then it will have 8 electrons and fill its octet. Each hydrogen, then, by sharing with one of the oxygens, will then achieve its stable duet, which is all hydrogen needs, and that makes it a stable compound similar to helium. You know, by definition, what you're looking at are things that are very similar in electronegativity. The difference is less than 1.7 and stuff that we'll talk about more when we get into bonding more. In reality, what we're looking at here are compounds that start with carbon as their first element, or have carbon as their first element, silicon as their first element, or this allows nonmetals to bond together, nitrogen and oxygen, phosphorus, all those anions that could not ionically bond because they have the same charge and they're both negative. And so it gives another variety. And one of the things we've always said is we look for that variety when you only have 92 naturally occurring elements and you have the billions of compounds that are out in the world. There needs to be different options to make that work. Anyhow, let's move on to the naming. So here we go. Covalent compounds share electrons. There isn't any ion formation. Only going to work with binary ones. So you can see all our formula here only have 2 elements. Okay. What makes this different? The naming is the same. So I'll start here with our first formula of NO2 here. I name the first element, and I'm not going to call it a cation because it is not an ion. But I name the first element, which is nitrogen. Just name it as I did for my binary ionic. Just name the first one as it is. The second one then, so it's nitrogen. The second one is oxygen, and again, just like with binary ionic, I change it to an ID ending. Okay. So it becomes nitrogen oxide. Now, the difference here and what we have to do differently is we need to use numerical prefixes to indicate how many of each element do I have sharing their electrons in this compound. And the reason I have to do that is there's no ion formation. So in ionic compounds, you knew the charge of the cation, you knew the charge of the anion, you would just then put together as many elements or atoms of each element as you needed until you neutralize that charge. Covalent compounds start out as neutral compounds, so you need numerical prefixes to indicate how many of these are put together and sharing. Okay. Now, you have on your periodic table cheat sheet a list of those, 1 through 10. The first one, here we have 1 nitrogen, and the first prefix would be mono. And here is our one exception. For the very first element, and very first element only, I do not have to write mono. For the second element, I always, regardless of what the prefix is, I always have to write it. For the first element, if it's just 1, I don't have to write mono. I would have to write anything else. If I had 2 or 3 or 4, I'd have to write the prefix, but I don't for the 1. I have 2 oxygens, that prefix is di. So this compound then becomes nitrogen dioxide. That's the proper way to write it. Okay. Same here. Write the first element. It's carbon. The second element again is oxygen, or in this case oxide. It's all binary compounds and an IDE. And then I'm going to look at the prefixes. I only have 1 carbon, so that would be mono, but because carbon is the first element, I don't have to write the mono. I do for the second one, so the second one, 1 oxygen, would be monooxide. I don't have to do a double up on my O's, so this becomes, oops, I didn't leave myself enough room, that becomes carbon monoxide. Okay. I think you can look at this one and get the idea what that is. Again, it's carbon. I do not have to write the numerical prefix to indicate I only have 1, only because it's the first element, so I do not have to say mono. For the oxygen, which is oxide, I have 2 of them. I do always have to use the prefix on the second element. So this is carbon dioxide. Di for 2, and oxide is what the second element is. Okay. So in writing the word formulas, that's actually rather straightforward. For the formulas, it is also quite straightforward because everything you need to write a covalent compound is told you in the compound. It says carbon. There's no prefix, so that means as the very first element, it only had 1 of them. It's chloride, so that formula is Cl, and the tetra tells me that I had 4 of those. Here I have trisilicon hexafluoride. Silicon is Si. Tri, now notice now I have a prefix on my first element. The only prefix I do not have to write is mono. I do have to write all the rest. So I have 3 silicon, and fluoride is fluorine, and it's hexa, so that means I had 6. Okay, so that's binary covalent compounds. It's rather straightforward. Now that has got us through all the ionic and the binary covalent naming that we've done. My last tip is going to be this guy. It is very simple to name all of the elements or all of the compounds when you know what it is, when you're told. When you have a sheet that says just name this whole list of binary ionic compounds or name this whole list of acids or whatever. The difficulty and the skill comes in making sure that I can identify the group of the type of compound it is when it's in a list with all varieties. So if I had a list of binary ionic, ternary ionic, transition metals, covalent, binary covalent, and acids or bases or anything along that line, could I look at that formula, could I look at that wording and write the proper formula, write the proper words of it if I had the formula, and do it correctly? That's where the difficulty comes in, and you need a guide like this one that I've given you in your packet. Now this is one where I follow the cation, as if you remember early in our naming notes we told you a couple things. Number 1, naming of ionic compounds, and in this case binary molecular also, is based on 2 things: the number of elements and the cation. The cation, when it's a hydrogen, makes it an acid. When it's a transition metal, makes it a Roman numeral. It gives those little twists. So I've given you this guide, or any other way that you can think about it. The first thing I would do when looking at or reading a compound is ask myself, is the cation hydrogen? And if I can answer yes, then I know I need to do that naming of it normally, and then look at the IDE, AT, IT ending and give it its acid name. If my answer is no, then I'm going to go here to the next question, and I'm going to say, is that cation a metal or a transition metal? It could be a metal that's not a transition metal. So is it a metal? And if I say yes, if I look at my box on my cheat sheet and I see that it's in that list with multiple possible cation charges, then I know that in the written format I have to use Roman numerals. You know, like the Roman numeral 2, for example, if it was copper 2. If I say no, it's not that, then I'm going to look and say, is the first element carbon? Is it silicon? Or is that first element an anion? Or are the two together? In that case, I'd probably be looking at just two elements. Is it an anion? Do I have what would be two negative elements together, because we know they couldn't do that and they would repel each other. So then if that first element is carbon silicon, or it's an anion, and I notice that I have two anions together, then I know it's one of those binary molecular compounds, in which case I write it just like I do a binary ionic with the first element, second element ID ending, and then I put in my numerical prefixes. I do not have to use mono on the first element, but I have to use every other prefix for first element, second element, along. If I go through all that and all those answers are no, then I'm just looking at my straight general binary ionic or polyatomic or ternary, whichever term you want to use for that, and I just name them accordingly. Of course, this is name the cation and then figure out what the polyatomic is and write that also with no change to the ending. They end in AT and ITE except for two exceptions. In the binary ionic, I know I have to write my cation, then my anion, and they all end in IDE. If that formula helps you, that's great. If you have another formula that you use to identify them, that's great. Either way, that is going to be the key to naming all these compounds throughout the year. So I would find a method. Okay? Thanks for joining us again. You can go to the Sophia page. I would imagine you might find a quiz on binary molecular compounds that you will enjoy.